Hey, good morning, everyone. This is a redo of yesterday's webinar meeting, because for some reason the Zoom cloud is delayed in providing a recording of that meeting. So I'm going to redo this so that I can get this video uploaded to you. And so those of you who weren't able to watch the webinar or want to rewatch it are able to do that. So we're going to start right away. You can see there's my background for this morning. I'm just experimenting with stuff. But let's just get right into it. I'm going to start sharing my screen. I'm going to turn off my video. The screen I'm going to share is the PowerPoint file. There it is. And so let's share it. And let's go to the start. And let's begin here. Okay. So like I said, let me stop my video. There we go. Like we said, these webinars are meant really for you to basically be able to keep learning physics content. And also one thing I learned that I'll share again on Thursday is it seems like it's also a good way for you to connect with each other as students. And help each other out both in physics and also maybe with things outside of physics. So I highly encourage you to do that as well. It would be a good idea to use your data booklet, to have your data booklet, your calculator, and your journal notebook to take notes. And there is a raise hand function on Zoom. So if you can locate that and experiment a bit to make sure you know how to raise your hand and how to use the chat function. You won't be able to use the chat function if you're looking at this video afterwards, but that's something that when you participate in webinars live, you have available to you. I also am going to publish the transcript of the chat. I'm going to try to publish the transcript of the chat every time so you can benefit from that. Okay. So again, priority number one in this time is to take care of yourself and your family and to be a good socially responsible citizen. I just want to emphasize that I miss you all, and I hope you're taking care of yourselves and your family, and everything else really, including anything related to this class, is a distant second. Also, don't worry if you can't write everything down. Like I said, this is the whole purpose why I'm re-recording this webinar. My goal is to keep these webinars to around 20 to 25 minutes. We'll have to see how that goes. I might have to adjust. I do tend to go through the slides a little quicker than I do in class, and I got feedback already that maybe I'm going too quickly, so I'll try and slow down somewhat. But remember, you can always watch these again and pause them if you're watching them after the fact. If you have questions, excuse me, put them in the chat function, and I will pause periodically during the webinars to look at the chat to answer questions. Okay, I want to talk about Zoom functionality. I want to talk about due dates, and then I want to talk about these sort of stellar concepts, astrophysics concepts you can see there, Hertzsprung-Russell diagrams. I want to talk about Henrietta-Leavitt, and I want to talk about Cepheid variables. Before we get started on all that, I just want to make sure you know that all assignments from now on are going to be turned in via Google Classroom. Do your best to make sure the images you upload are in focus. If you happen to have tech issues that prevent you, or any issues that prevent you from submitting work, please just send me an email, remind.com. And I just want to emphasize that I will not penalize any student who has, for whatever reason, legitimate issues in turning in work. I won't assign any sort of late penalty. But please try and continue to turn in the work. I do want to apologize in advance. This is a picture of our dog, Dobby. She is a 25-pound Australian Labradoodle. I'd love to say she's a puppy and she doesn't know better, but it's not true. She's like 8 years old. And she tends to bark a lot at people and things. Squirrels are her nemesis, and they tend to just always be around our house. So you're going to hear her for sure at some point, and you're probably going to get annoyed with her because she's barking so much and disturbing the audio. So just apologies in advance. In terms of Zoom functionality, you are muted, and I've turned the video off for you guys. We'll see how that goes. We might experiment with that a bit. Again, use the chat function if you want to pose a question to me, if you want me to go over something. Also, if you want to pose a question to another classmate, you can do that. I believe you can actually message each other privately, and you don't have to message the whole group. But let's use this as a forum for all of us to help each other learn physics. And again, if there are other ways you want to connect with other students outside of physics, I'm totally fine with that. Let's please just keep it PG. And there are ways to raise your hand and lower your hand, and I might ask you to do that every once in a while. Also, I'm going to try experiment with the polling functionality. Apparently, I did that in the first webinar just to kind of see how it goes. It's a little clunky, but we'll see how that goes. Also, if you find something that's really useful to you in terms of Zoom functionality, please share it with others. say something about it in the chat function. Also, you can put links in the chat function. So that's another thing that I would just want to encourage you to do. If you find helpful links in terms of learning the physics that we're talking about here, please feel free to throw them in there. Again, if you miss a webinar meeting, don't worry. All these recordings are being uploaded to the class website. And I said later that same day, but I'm going to just say within 24 to 36 hours because the Zoom website seems to be having some difficulties with timely recordings, offering timely recordings. Here you can see the due dates. I have put on Google Classroom an assignment for problems at 5.3. If you didn't turn in a paper copy, then turn it in via Google Classroom. Astrophysics podcast assignment is due Wednesday, the 18th. And then problems at 6-1 is due Friday. And then you can see looking ahead after spring break, well past spring break, problems at 6-2. Our essential question for today: how can we classify stars? And how can we determine the distance of stars using methods other than stellar parallax? So let's keep that in mind as we move along. Okay, so let's jump into the science. And I first want to start with a review of what we talked about the very last day, or in the last week that we had each other in class. Remember, the forces on the star, the big forces that we want to make sure we remember is we have gravity pulling two particles with mass closer to each other in the star. That's pulling all that mass closer and closer inward, so to speak. And competing with that force are gas pressure and radiation pressure. We often call those thermal forces. This is something we talked about last class, and those are the predominant forces on the star for the majority of its life. We talked about these two cycles, the stellar evolution, the top there, the life cycle of a low mass star, and then the life cycle of a high mass star beneath it. Main difference is, right, when we get to the red giant or red supergiant phase, high mass star just becomes that much more bigger. And then also the high mass star undergoes a further, more elaborate fusion process where it keeps fusing elements all the way up to iron 56. Whereas the low mass star really just stops with fusing helium or carbon. The low mass star obviously is going to create a planetary nebula, and then it's going to transition to become a white dwarf, whereas the high mass star is going to create a supernova event where all the elements greater than iron 56 are created. And then from there, it's a question of whether it'll become a neutron star or a black hole. I do want to emphasize, by the end of this unit, you should be able to explain these items that we've talked about a little bit in complete sentences: Jeans mass or Jeans criterion, what we talk about electron degeneracy pressure and neutron degeneracy pressure, the Chandrasekhar limit, and then the last one I want to talk about more because I went over it really quickly towards the end of class, and I think even in one section I may not have reached this slide. So I want to talk more about the Oppenheimer-Volkoff limit. So that's what we're going to talk about here in the next slide. The Oppenheimer-Volkoff limit. If you remember, we're talking about the lower right corner of the life cycle of a high mass star. So the supernova event has blown off the outer layers, and what remains behind at that point is a neutron star. And with a neutron star, what's the force that's counterbalancing gravity? Well, that would be what we call neutron degeneracy pressure. And that is basically the neutron's version of the Pauli exclusion principle for electrons, meaning that no two neutrons can occupy the same quantum state. And so what happens there is that becomes the outward pressure that counteracts gravity. But there was two gentlemen, Robert Oppenheimer, a very famous person, who worked on the Manhattan Project, but also did some studying in astrophysics. And another physicist named Volkoff, don't know his first name. They did some pretty complicated math, and they basically realized that there's an upper value at which a neutron star can no longer be stable. In other words, the neutron degeneracy pressure cannot withstand the massive gravitational force pulling all this stuff inward. And if a neutron star has or acquires that mass figure, then it's going to no longer remain a neutron star. Eventually, it's going to turn into a black hole. That limit, that Oppenheimer-Volkoff limit, is somewhere between 1.5 to 3 solar masses. In other words, if you have a neutron star that has a mass greater than 3 solar masses, it is for sure going to transition and eventually become a black hole. If it is less than 1.5 solar masses, it is going to for sure stay as a neutron star. And if it's in between those two, then it could go either way. So that's the Oppenheimer-Volkoff limit. What else do supernovae do? Remember, the supernovae blow off those outer layers, and in some regions in space, those outer layers are going to create these huge regions of clouds of dust and gas. And dust and gas in a big region of outer space is what we call a nebula, right? And we know nebulas are where the stars are born, the stellar nursery, so to speak. And so that's where we kind of come back to the beginning over here with the protostars, and this cycle begins all over again. Kind of neat, isn't that neat how it kind of circles back and just starts all over? Something to think about, something to ponder. Okay, I promised at least 2 stories or puns, and here's the first one. You know, I'm from a large family, and I'm one of 7 brothers and sisters. And you know, the other day, one of my brothers, he knows I study and teach physics. So he looked at me and he said, you know, I had a question. He said, you know, can you explain to me why planets, when they're so far away from the sun, you know, they have a certain radius, a certain speed, and in a certain time period, they sweep out a certain area. And then when they get closer, they go faster. But if you map the same time and you measure the radius or the area that they sweep out, it tends to be the same. Why is that? And so I looked at him and I got really frustrated because he's always asking me these questions. And I said, look, what do you think I am? Do you think I'm my brother's Kepler? Get it? Kepler, brother's keeper. Anyway, as I said, it's kind of hard to tell these jokes when you don't get a response. But anyway, okay. Hertzsprung-Russell diagrams is what we're going to talk about next, and then that's going to lead into talking about Henrietta Leavitt and Annie Jump Cannon and the Harvard computers and the Cepheid variables. We're going to finish up. So this is another sort of review slide. I just want to recap some of the things that we can already determine about stars. Remember, brightness is what we can determine in our telescopes, easily observed by the electromagnetic radiation, the waves that are coming in there from those stars. We can use stellar parallax to measure distance in certain cases. If we know the brightness and the distance of the star, notice from that formula over there on the right, we can get the luminosity, which is the power generated by the star at its surface. And if we can determine the maximum wavelength of the radiation that's coming to us, the electromagnetic waves coming to us, which we can usually, then that gives us an estimate of the max temperature of the star by the Wien's displacement law. And then finally, if we know temperature and we somehow know distance, then we can use the Stefan-Boltzmann equation to figure out the general size of the star, meaning the radius. So isn't this amazing? Let's keep going because we can learn even more about stars. So if we go back in history to the late 1800s, early 1900s, there were telescopes and there was a bunch of data and just images coming from telescopes. And so much so that scientists really didn't know what to do with it, and they couldn't really easily make patterns of what they were seeing. You know, all these different stars, all this different data coming in. So what do we try and do when we look at all this data? We obviously always try and classify it. So they tried to classify the stars and identify which stars are brighter, which stars seem to be doing this or that. And in doing so, they hope to find some patterns that would help explain or help us understand better what's the nature of the universe. And again, that's at a fundamental level, that's what, at least in physics, and certainly in all the sciences, I would say we're trying to do, is to make observations, conduct experiments, to figure out what the heck is going on in the world and what are the fundamental laws, fundamental ideas that govern how things happen or why things happen. So one thing I want to just emphasize really clearly here is, as usual, our history sometimes recognizes some people quite significantly and minimizes the contributions of others at the time. And this was no doubt the case with astronomy and astrophysics in the late 1800s, early 1900s, because it was very, very gender biased, misogynistic, you could say even. Only men could operate the telescopes, the actual equipment. But they needed help. They needed help in terms of people to analyze these thousands and tens of thousands of images that were coming from these telescopes and that make some sort of sense to them. So a lot of this work was done by women, and at Harvard Observatory, it was done by a group of women became known as the Harvard computers. And as you can see there in that room, what are they doing? They're taking these photographic plates that are generated by the telescope images, And they are putting them in this sort of apparatus, and I don't remember the name of the apparatus, but it basically allowed you to flip back and forth between successive images of the night sky very quickly, almost like a flip book. And in doing so, they were just trying to measure and understand the things about the stars. Are they getting brighter? Are they getting dimmer? Which stars which? How can we classify and identify patterns in this stuff? And so I'm going to talk more about two specific women later on here, but I just want to recognize that this was really an important and valuable and often overlooked contribution. So with the help of all these women, these Harvard computers, and other people around the world, around 1913, there were two astronomers, Hertzsprung in Denmark and Henry Norris Russell in America, and they basically came up with this sort of way of representing what we know about stars. It's called the Hertzsprung-Russell diagram, and you're going to see it here in the next slide. And what it is, it's graphing luminosity on the vertical scale. Remember, luminosity is the power of the star at its surface. And it's graphing temperature on the horizontal scale, how hot the star is. There is something you're going to see called spectral class, and you don't need to know about it anymore, but it used to be the way that was that stars were classified, and it had this letter scheme. And frankly, I'm not going to say much more about it. If you want to read up more on it, you can, but it's not something I would quiz you on or test you on. It's really not used all that much anymore. Okay, so here's what the Hertzsprung-Russell diagram looks like in general at its like most basic. I'm going to show you a more elaborate picture here next slide, but let's just point out a few things. If you look on the vertical scale, L over L with a little circle around it, that is relative luminosity. And what is it relative to? Well, remember, I said at the beginning of the unit, oftentimes we are classifying stars and referencing their characteristics to the characteristic of our closest star, the sun. And that is the case with this diagram. L with that little symbol, that little circle with a dot in the middle is our sun, okay? So this is measured in terms of units of how much more luminous the stars are compared to our sun. So any star on this line right here has the same luminosity as our sun. This horizontal line that I'm drawing with my little thing. Any star on this line here would have 100 times the luminosity of our sun, 10 squared, etc. On the horizontal scale, you have temperature. And temperature is measured, as you can see there. It looks weird, right? Because it's also log scale, but it goes from highest to lowest. Why is that? Well, the original Hertzsprung-Russell diagrams didn't plot temperature on the horizontal scale. They actually plotted wavelength. And if you remember, wavelength and temperature by Wien's displacement law are inversely proportional to each other. So because of that, that's why we've just kind of kept it this way. These letters up at the top here, that's the spectral classification you don't need to know anything more about. And so what you can see here is there's this diagonal along the, in the diagram, which is where the main sequence stars are. Remember, those main sequence stars are those stars that are combining hydrogen in their core to form helium, fusing hydrogen to form helium. And remember, this is where a star spends a large majority of its lifetime in this main sequence. And you can see up here to the right, the giants and the supergiants. This is the spot where the stars go after they conclude fusing hydrogen and they start fusing other elements. And you can see down here, the white dwarfs is where the lower mass stars eventually end up when they no longer have basically, when their fusion is no longer occurring. Okay. You might ask, well, where are the neutron stars and where the black hole? Neutron stars and black holes do not appear on this, because remember, this is a sort of guide to luminosity, which is power output. And so those stars are basically, well, a black hole isn't a star, right? It's really not luminous at all, so it wouldn't appear on here. And a neutron star, its luminosity is really quite low, so it would not be on the scale. Like, it'd be way, way down. Okay, so if we keep going, this is another, this is a more elaborate way of looking at it. By the way, our sun is right here. Very average star. We're quite average. Being average is okay. So I just kind of talked through everything in this slide, so I'm not going to spend much time just rehashing this, but you can just see different things. There's Betelgeuse up here. And yeah, if you want to take a look more at this and copy down all you see here or some of the information you see here, feel free to pause the video. What I will say is I have seen IB questions. You could be tested. I could test you by showing you a HR diagram, asking you to fill in certain blank areas, identifying where the white dwarfs are. Also, I could ask you a question of kind of trace the evolution of our sun, what we think is going to happen. And so you should be able to do that sort of thing, and we'll talk more about that. Okay. This is a very quick, just sort of, I want to show you the original data that Henry Norris Russell was working with, and this is the original paper that he published his thing in 1912, I believe. So you can see there, what I find fascinating about this is just a huge testament to like human tenacity and just humans' abilities to kind of pick out patterns out of a data set that might, if I looked at this data set, honestly, I'm not sure I would have picked out the pattern that Henry Norris Russell did, but it's just fabulous to see what scientists can do. And those of you who had an IA where you had a data set, you're like, what the heck is going on? You can appreciate that humans really work at this really difficult problems. They can work at it for a long time and achieve some amazing results. Okay, I want to talk about two specific Harvard computers who should get a lot more credit than they typically do. One person is Annie Jump Cannon. As you can see there, that's a picture of her. And again, this is her looking at these photographic plates day after day, week after week. I just want to emphasize how tedious this work was. If you can think about just staring at these images one after the other and picking out the most minute differences from one image to the next as they tried to classify and understand what stars were doing. It's really just an incredible feat what they did. For example, Annie Jump Cannon is recognized as single-handedly classified more than 250,000 stellar spectra, meaning looking at these images and understanding more about the stars. And if I remember, the stellar spectra is those lines, remember those lines coming in that indicate different sort of elements coming from the star. The other person I want to talk about is Henrietta Leavitt. Henrietta Leavitt graduated from Radcliffe. Radcliffe was the women's college in Harvard for women because Harvard was only a men's-only institution back then. But she couldn't get work at any observatory actually performing observations on telescopes because, again, women weren't allowed. So she goes to work with Harvard computers, and she does a ton of work on something called Cepheid variable stars. We're going to talk more about what these stars are in a moment. But the biggest contribution she makes, and it is a huge one, is that she makes a connection that the periodicity of these stars' brightness is got a relationship to the luminosity. And I'll talk more about that here in a few slides. So let's just take a moment to recognize Annie Jump Cannon, Henrietta Leavitt, and all the other women in the Harvard computers who did this incredible amount of work. One other really interesting story about Henrietta Leavitt. So in 1923, these Swedish physicists inquired with Harvard. They said they wanted to take a look at her work because they wanted to possibly nominate her for the Nobel Prize. Unfortunately, she had passed away a few years earlier because she was a victim of cancer. And it's very sad because the Nobel Prize, I believe even to this day, cannot be awarded to anyone who has died. So she was unable to be nominated or possibly receive the Nobel Prize because of that. Okay, if you're watching this after the fact and you haven't watched these two videos yet that I put on the pre-webinar stuff, please pause and go take a look because they're very, very helpful to understand what we're talking about here. Let's continue now. Second story. I don't know if you realize this, but the other day, this astronaut, well, this was more than the other day, it was a couple of decades ago, but anyway, an astronaut basically went to eat a restaurant on the moon. Came out and people asked him about, asked her about how was the restaurant, kind of wanted to give it a review, and basically turned to the press and said, the food was great, but the place just had no atmosphere. Haha. Okay, this last thing we're going to talk about today is Cepheid variable stars. Like I said, Cepheid variable stars are a very special type of stars. And if you look there at the top right, this is obviously a dramatization of what they look like. What happens is if you take successive images of Cepheid variable stars over several days or even months, you will notice that their luminosity changes over time, their brightness. It increases sharply and then falls off. And the best way to look at this is to look at a graph down here. This is a typical Cepheid variable star sort of graph. If you can see luminosity is on the vertical scale and period is on the horizontal scale. And so what it'll do is it'll go up really quickly and then decrease gently, and then up again really quickly, and then decrease gently. And it does this in a predictable periodic way. So a Cepheid is basically pulsing regularly, expanding, contracting, and I will talk next time about why it does this. But what you need to know is that a luminosity oscillates with regularity, okay? And so here's what Henrietta Leavitt did. She basically was looking at at a group of these Cepheids in a specific galaxy. And so this is a key idea. She was looking at all these stars that are pretty much about the same distance away from Earth. Okay, so she didn't know what the distance was, but she knew they were all in the same spot, about the same distance. And so what she started to realize is, so in other words, the brightness of the object, the brightness of these stars wasn't affected by its distance from the Earth. It was basically just affected by its periodicity. And what she found was, if she plotted the period, you can see down there on the lower right, there's a log scale. If she plotted the period of the star on the x-axis and plotted the relative luminosity compared to our sun on the y-axis, you got a very fascinating curve. You can see there, you got basically a sort of a relationship you can see there, which is linear on a log scale. So this is incredible. This is an incredible sort of feat of hers. And she published this in 1912. And what's interesting is she can only publish the fact that she's got this relationship, that period and luminosity are related in this way. So Cepheids with longer periods are intrinsically more luminous than those with shorter periods. But she can't put numbers, she can't put exact numbers on the vertical scale, okay, because she doesn't know how far away, she's working, I think, in the small Magellanic Cloud, and no one knew how far away the stars were. Okay, so this is key. So what she does, she publishes this paper, and then of course another scientist looks at her work and builds on it, and I believe it's actually Hertzsprung who says, well, hey, wait a second, I have information about Cepheids much closer to us that I've been looking at, and I know the distance to those Cepheids, so I can apply your information about the relative brightness and the fact that I know the distance to these Cepheids to actually basically create something called a standard candle. Now, this standard candle is a really important concept, and I just want I want to kind of emphasize a couple things about it. You'll hear this term a lot from here on forward. And what you want to think when you hear standard candle is you want to say, or you want to think, okay, a standard candle is an object in astronomy. It's a star, basically. It's a star that I know the luminosity to it, okay? I know its luminosity regardless of how far it is from the Earth. Somehow, through some other means, in this case with Cepheid variables, because of the periodicity of how it's brightening and dimming, I know how luminous it is at its surface, okay? And if you know that, you're going to see here in the next slide, that's huge because it allows us to then determine the distance to it. And so let's just go right at it. So if you look at this equation right here, this is the equation we've been talking about for a couple of sessions. The apparent brightness, remember this brightness is what you measure in your telescope, right? The capital L is for luminosity. That's the power of the star at its surface. Now remember, we just discovered with Cepheid variables, there's a way we can calculate it without knowing the distance. So notice if we know B and we know L, what is the only variable left in this equation? It's D, which is the distance from us to that star. So this was groundbreaking. This was incredible because now we had another tool, a very important tool in an astronomer's toolbox to figure out the distance to a certain type of star. And if you can figure out the distance to that star and you know other stars are nearby it, then you can basically figure out the distance to certain galaxies and stuff. So let's walk through one example here that was really important, groundbreaking in the world of astrophysics. So Cepheid star V1, around that time, I think it might have been a little bit later. I think it's in the 1920s, but I could be wrong. So if V1 has a period of 31.4 days and apparent brightness of 1.2 times 10 to the 15th watts, determine the approximate distance from the Earth in light years. The luminosity of the sun is given right there. By the way, that's in your data booklet as well. If you're watching this after the fact, please feel free to pause the video and try this problem yourself. In fact, I would encourage you to do that. Okay, now let's move on and see what the answer is. So let me walk through this. Notice in green circles, I've kind of showed you what I did first, second, third, and fourth. So first we have that brightness luminosity relationship, and all I did is I solved that for distance, d squared. And then I go into the graph here and notice that with this blue line, did you see that blue line? I go in at 31.4 days, and I go until I go up to the type 1, and I come across here, and notice it comes out at just above 10 to the 4th. Remember, 10 to the 4th is 10,000. So I'm just going to call that 2 times 10 to the 4th, about 20,000. And that's down here is what I'm doing is I'm saying that's 2 times 10 to the 4th, but basically the units here are saying that's 2 times 10 to the 4th times the luminosity of our sun. You know, the luminosity of our sun is 3.85 times 10 to the 26 watts. So if I take 2 times 10 to the 4th times this number, I get 7.7 times 10 to the 30th. And that's the luminosity of the star. I plug that in here on step 3, divided by 4 pi times the apparent brightness. And I get a d squared value of about 5.11 times 10 to the 44th meters squared, or 2.26 times 10 to the 22nd meters. Last part of this problem is I don't want the answer in meters, I want it in light years, so I come down here and I convert it from meters to light years. And you can see here, I get a value of 2.4 times 10 to the 6th light years for Cepheid star V1. This calculation, performed in the early 1900s, had a profound effect on astronomers and astrophysicists' understanding of the universe. Why is that? Let's go to the next slide. Because this confirmed that that star was about 2.4 million light years away in what is it we now know as the Andromeda Galaxy, which is much, much more distant than the 100,000 light year diameter of the Milky Way galaxy, which we've talked about before. And this is important because the prevailing wisdom of a lot of leading astronomers at the time was the Milky Way galaxy was it. That was the only galaxy. That was the extent of our universe. And so when this measurement came across or was discovered, it presented really strong evidence that the universe was much, much bigger than the Milky Way galaxy. And again, this was much against the prevailing wisdom at the time. In fact, there's an interesting quote. Edwin Hubble sent a letter to another famed astronomer, Shapley, Harlow Shapley, and Shapley was a big proponent of the Milky Way is all that there is in the universe. Shapley turned to a colleague and said, "Here's the letter that destroyed my universe." Interesting. We have to think bigger. We have to think broader in this world often. Okay, so the last slide is just a couple things. If you haven't done the after webinar survey yet, please do that. You can see the tiny URL link is there. There's also a link on the blog. The next webinar is Thursday, the 19th at 11. I've already put pre-webinar activities on the blog. I put it yesterday, Tuesday evening, the 17th. I'm not going to stay after because no one's watching this, but I usually try and stay after for a few minutes and answer remaining questions. You can post them in the chat room. And at the bottom there, we all need ways to laugh during this time period. And I found these 20-second hand washing parody songs really funny on YouTube. So I recommend you check those out. It's about 3 minutes worth. Okay, thank you so much. I'm going to end the meeting now.